Can a system conserve angular momentum but not linear momentum? These are interesting kinds of questions that sometimes get you really thinking about things, because one might assume, well, maybe linear momentum needs to be conserved in order for angular momentum to be conserved, right? Is angular momentum like a special case or something? But the answer is that's not the case. And it turns out a system can do this. It might take a little bit of thinking to figure out what type of system. It turns out there are systems that have both angular momentum conservation and linear momentum conservation. Both of these ideas are useful in collisions. We've already seen how linear momentum can be used for collisions. One example where both might be conserved is like, what if I had an object here, pseudo round object there, and it is coming in, and then here's another object, and what's going to happen is maybe there's like Velcro on these two objects, and when this one touches this one right here, it's going to stick to it, right? And so the final state for a system like this would be the one object kind of stuck to the other object, and they would be moving. If they were equal mass, I think their final speed, linear speed, would be half of what it initially was in order to conserve linear momentum, but they'd also wind up rotating, which might make sense, right? Because I mean, if you kind of imagine this in your mind, right, when this thing hits here, it's going to kind of pull on that other one, and the result is they wind up spinning around each other. That one's kind of a complicated one to analyze, and it doesn't really answer this question very well, because this is one where I said both linear momentum and angular momentum are conserved, and we're looking for a system where angular momentum is conserved but not linear momentum. So let me change things a little bit. Let's say instead of two kind of roundish shaped objects, let's say I have a dart here. Okay, and this dart is just flying through space, and you know, this could be because somebody threw it here on Earth, but I'm going to say it doesn't really matter. This thing's just flying through space, and it's going to hit a very special kind of target. This target might be a rod, or maybe it's something that has some more of a height, so maybe it's like a door, but this rod or door or whatever is fixed to swing around a point right here. So I'm going to say that is like what I've referred to earlier as like a fixed point. You could also say maybe it's a hinge type of system, right? And what's going to happen in this case is the dart is going to hit this thing, and it's going to wind up swinging. So I don't know if I can draw this, but I'll do my best. So there it is. It now is swinging around this way, right? And the dart would be stuck in it wherever it impacted. So something like that. Looks like my dart got squished a little bit there too. Also, let me fix that arrow there. That's meant to convey rotation, right? Okay, a little bit better. All right. For this one, it turns out you could apply angular momentum conservation to the system of the dart plus this target, whether it's a rod or maybe it's like one of those swinging doors, kind of like you used to have in the Old West on the bars, you know, that kind of thing, like that just swing freely when you hit them, something like that, or a door that's not latched, right, like a modern door. Angular momentum is conserved though, because for the system of the dart plus that door, there is no torque on this system. There are forces applied to the door at this hinge. They are large and they are non-trivial, but if that is the rotation axis that I define for this system, then those forces do not apply any torque to it. Any forces exchanged between the door and the dart are internal to the system, so that's kind of analogous to how we looked at linear momentum conservation applying to collisions. I mean, there are forces involved, but they were internal, provided we made our system involve all the objects that, or the two objects that were colliding. And that's kind of what we're saying here, but with this extra sort of added hinge here, that spoils the linear momentum conservation, because there's definitely a pretty large force actually applied to it. I think when the dart impacts it here, there'd be a really large force that kind of in the opposite direction that the dart's force would be applying to the door. Maybe the net force might be very close to zero, maybe not exactly zero, but that applies no torque. But then the impact force of the dart does apply a torque to the door, but again, that's an internal force causing it to start rotating. So the way to analyze a system like this is to say, well, can we associate some initial angular momentum with this object that is moving linearly here, the dart, given that the rotation axis is this fixed point? And then if we set that equal to the final amount of angular momentum here, maybe we could answer questions like how fast would it be swinging, given that we knew things like the mass of the dart, the mass of the door, and how fast the dart was moving before it impacted it. So I almost stopped the video, forgot. We should check the answer, right? My answer was yes, and then very complicated, but the slide just says yes.